So hello, everyone. Welcome to the second Ukraine seminar in fundamental physics, and thanks to all of you for joining us. Today we have a very interesting talk on cosmological topic, and our speaker is Professor Tamara Davis, an astrophysicist at the University of Queensland, Australia. She is a scientist with over 2 decades of experience in supernova and cosmology and large-scale structure. And let me say a few more words about our speakers. So Tamara Davis did her PhD at the University of New South Wales on theoretical cosmology. Then in 2004, she went to the Australian National University in Canberra to work with Brian Schmidt on supernova cosmology. Then she got a postdoc position at the University of Copenhagen. And finally, in 2008, she ended up at the University of Queensland, where she started work on large-scale structure cosmology. Professor Davis led the dark theme in the Australian Centre of Excellence for All-Sky Astrophysics. She is currently leading the Australian Dark Energy Survey, the so-called AUSDES. And she was recently announced as a deputy director of the upcoming Center of Excellence for Gravitational Wave Discovery. She is an avid communicator of science, and now she is a regular guest host of the Catalyst Science Show on ABC TV. For example, of that episode, Black Hole Hunters, which won the Science Communication Award of the American Institute of Physics. And today's talk is entitled Cosmology as a Probe of Fundamental Physics. In this talk, Professor Davis will summarize the main methods by which astrophysicists are exploring the world around us and pushing the boundaries of known physics. And she will discuss the existing tensions that are emerging between different cosmological probes. Dear Professor Davis, thank you very much for agreeing to give a talk at our seminar. And especially because this is a very late hour in Brisbane. So please, the floor is yours. Thank you very much.
Thank you so much. Thanks so much for inviting me to give this talk. I'm very glad that I'm able to give this talk in this Ukraine seminar in fundamental physics series. I'm really glad that this initiative has been started up so that we can have these discussions. I'll share some slides in a moment, but before I do, I just wanted to have a quick hello to the audience because I wanted to make sure sort of who I'm talking to. I understand that there's lots of, hopefully lots of physicists here. Some will be astrophysicists, some will be not physicists, some might not be physicists at all. So can I get you to put a thumbs up if you are in astrophysics? If you have a reaction, you can either put your camera on or do the little thumbs up in the thing. I see a few thumbs up popping up. Okay, and so thumbs up if you are now. So now everybody who is in physics but not astrophysics, if you could put your thumbs up, then I'll get a sort of a sense of who the audience is. Cool. So there's more thumbs in there and stuff. So okay. So what my plan is today is to give you a little bit of a lightning tour of introducing some of the measurements from cosmology, some of the exciting things we know from cosmology, but also the conundrums and tensions that are evolving. So let me share. We'll go this way. Hopefully that works. Is that all good?
Yeah, perfect. Thank you.
Great. Okay, so I could start with this one because I spend a lot of time as a cosmologist looking out at the sky and looking and trying to figure out how bright dots are. This figure that this image in the background that you may recognize here, this is the really cool image from the James Webb Space Telescope that shows lots of clustering of galaxies and lensing of galaxies in the background, but this like beautiful scape of a huge number of galaxies that we can see with things like the James Webb Space Telescope. And it's really the power of the telescopes that we have at the moment that has made it such a golden age of astrophysics, so that we're able to learn so much about it. Lately, I've been starting talks by saying that there's sort of a couple of different ways in which we test cosmology, putting it extremely simply. The first way, measure the expansion of the universe, change time. So just look at the average features over the sort of, assuming the universe is homogeneous and isotropic everywhere. And then there's looking at the details, looking at the clumpiness, looking at the motions and stuff inside of that big homogeneous expansion. That would be the inhomogeneous measurements that we make, sort of width of structure and just the structure itself. Now, the first, a classic one for the homogeneous case is looking at the expansion of the universe with type 1a supernovae. And the inhomogeneous case, as I said, is sort of this gravitational lensing, which I'm showing in the background, and I'll come back to, is one of the sort of classic ones for the inhomogeneous universe. So we've got a huge amount of data now. As I said, it's a bit of a golden age of astronomy. The quantity of data, the amount of amazing telescopes that we have measuring across all sorts of wavelengths of light, even looking at particles that are coming from space, so cosmic rays, etc., not just light, and also these days gravitational waves. And putting all of these things together, we have the audacity to put tables out like this as cosmologists, where we're quoting uncertainties to better than 1% precision about a whole bunch of parameters that we used to get heckled about for not knowing very well. So I remember when I started doing cosmology in the 1990s, it had a bad reputation for people would laugh, like, you don't even know how much matter there is in the universe to a factor of 2. And these days, we're talking about having it to 1% precision. So it's been a huge change in the last sort of couple of decades. Now, we have this amazing standard model of cosmology that I'm talking about here, but it involves a couple of weird things. The first one is that there's about 25% of the universe, of the energy density of the universe, is in dark matter. It pulls, it's clumpy, it holds galaxies together. Whereas 70% of the energy density of the universe appears to be in some form of what we call dark energy, which is accelerating the galaxies away from each other. It's accelerating the entire expansion of the universe. It might be the energy of the vacuum. It pushes, it's smooth. So this is a couple of weird things that indicate that we don't really understand 95% of the universe. So while we have a really nice standard model that matches lots of data, it does have a couple of things that we still don't really fully understand. Of course, the dial really raced through a couple of things about like how dark matter was discovered and dark energy, to set the scene for the tensions and things that are going to come up in a second. Now, the expansion was discovered in the late 1920s with Lemaitre and Hubble. And it was hot on the heels of that discovery that the first papers on dark matter came out. So the first paper on dark matter was by Fritz Zwicky, which was in 1933, and was done by measuring the velocity of galaxies, all galaxies, and noticing that they're moving too fast to be explained by the expected mass in those galaxies. The sort of real big sort of flag that everybody knows about is the rotation curves of galaxies, where you would expect galaxies to rotate like this version on the left, where the outskirts are rotating much slower than the inner parts of the galaxy, because it drops off, the gravity drops off. But what we see is that in spiral galaxies, the outskirts are rotating with the same speed as the inner parts. So that's very weird, because there shouldn't be enough gravity in this galaxy to hold those outer parts of the galaxy together when it's spinning like this. So this was sort of the point where everybody got really serious about dark matter and said, hold on, there's something there that needs to be explained. So we think there's some extra matter in there, actually. Of course, it could be that our theory of gravity is wrong, and that needs revision. These days, we think it's probably dark matter is probably a sort of particle, but we still are open to the idea that our theory of gravity needs revision. So the discovery of dark energy had to take a lot longer. And it came about in the 1990s when people were trying to figure out whether the universe was going to recollapse or expand forever. And it required the discovery of a cool type of standard candle. And that was the type 1a supernovae. So this is an exploding star that at its peak brightness is can outshine all of the hundreds of billions of stars in the host galaxy. That makes it super, super handy because as long as we can see galaxies, we can see supernovae. So that means we can see them really far away and measure how fast the universe is expanding back then compared to how fast it's expanding now, and use that to measure the expansion of the universe. So in the 1990s, a couple of teams got together to do this. This was Brian Schmidt in the red corner, was leading the high redshift supernova team. Saul Perlmutter in the blue corner was leading the supernova cosmology project. Here they are pretending to fight at a conference. And lo and behold, at the end of the 90s, both teams found that the universe is actually accelerating at the moment. And in detail, it decelerated to start with, and it's accelerating right now, the unknown cause of which is dark energy. Now, hopefully most people are familiar with those. I just thought I should give the lightning fast tour of those to start with, though, just to set the scene and remind people that the dark energy actually solved a whole bunch of problems in cosmology. All of those embarrassing problems I was talking about before, where we couldn't figure out what the matter density was of the universe to within a factor of 2, etc., sort of got solved by dark energy. Because in the 90s, there were several big problems. For example, the age of the universe. It appeared that if the universe decelerated to its current expansion rate, that some of the stars in the universe were older than the universe itself. And hey, some people thought that was a problem. On the other hand, there were too many galaxies at large distances. People who were just doing like sort of census of galaxy measurements and counting numbers of galaxies, etc., at high redshifts compared to low redshifts, just were finding too many at large distances. And the other one was the mass, as I've mentioned. We had really good theoretical reasons to think that the universe should be flat, but we only could find about 30% of the mass needed to make it flat. And that 30% included all of the dark matter. Now, dark energy came along and solved all of this. So in the first case, for the age, if you plot the size of the universe versus time and normalize it to the slope at the present day, which is what known as the Hubble constant, if it decelerated to that point, then it hits this zero size axis at a shorter time than if it first decelerated and then accelerated. So here's just a couple of universes that I've chucked in. So if you have an accelerating phase right now, the universe is older than it would otherwise have been. And that solved the age of the universe problem. So now stars are younger than the universe that hosts them, and everybody's happy about that. The number density of galaxies is the next thing. So the too many galaxies at large distances was not because people were counting galaxies incorrectly, but just because the volume in the denominator was incorrect. Once you include the acceleration of fact, the number of galaxies divided by volume of space, the volume went up, and thus the density went back down to the reasonable amount. And you could actually argue that there was a couple of papers written in the early 90s about this that claimed that the way to explain what they had been seeing was actually dark energy or the cosmological constant. So you really could argue that they were the ones that deserve to have been given the discovery of dark energy rather than the people who were doing the supernovae. But it wasn't quite clinching enough that people were really convinced. But it certainly set the scene. All of these set the scene for why dark energy was accepted so quickly. And the mass, once you added 70% dark energy of the universe, then the 30% of dark matter and normal matter made sense because it all added up to enough energy density to make the universe flat. And so again, everybody was happy. Now, after the supernovae discoveries were made, the cosmic microwave background measurements started to get particularly strong. And these days, the sort of most precise of the measurements that we have of cosmology comes from the cosmic microwave background. So it acts as a standard ruler. So unlike the supernovae, which were standard candles and object of known brightness, the sort of hot spots and cold spots in this map of the radiation of the Big Bang act as rulers, objects of knowns. And we use those to measure a whole bunch of details about the universe. This is the beautiful plot that came out from the Planck Space Telescope. And this is the strength of fluctuations as a function of their separation on the sky, where it's a Fourier transform. So the left are large scales and the right are small scales. And I remember when I saw this plot come out, I sort of gasped and I was like, oh, wow, isn't this beautiful? Because this is, the red line is the model that has the amount of dark matter that you see in galaxy rotation, the amount of dark energy that you see from supernovae, etc. And the blue data points are the data with error bars. You can see there's a couple of where you can actually see the error bars, but for the most part, the error bars are so small that they're smaller than the points. And it's still fit to the model. This was the more precise version, so the model is tuned exactly to the CMB. This is the one that fits the CMB data best, but it's consistent with all of the measurements that went before. And to show you how sensitive the cosmic microwave background is to dark energy and dark matter, I've just attempted to roughly overplot what would happen if you took the dark energy out of this measurement. And you can see how bad a fit that becomes. And even worse if you take the dark matter out. Now, you can tune the parameters, like other parameters, to compensate for the lack of dark matter in some sense, but you can't get as good a fit by any means as what you see for the with dark matter in it. So this is a beautiful picture, and we're really happy that we have this standard model cosmology with dark matter and dark energy, sort of basically fitting almost everything that we observe. But recently, say the last decade, some cracks have started to emerge. And this is why we use the word tension, or this is where we start to use the word tension, because there is some tension between some different measurements in cosmology at the moment. So the first tension is with H0. So H0 is the expansion of the universe at the present day. Hubble's law is the velocity is proportional, or the Hubble-Lemaitre law is that velocity is proportional to distance, and h is actually the rate of change of the size, scale factor, the size of the universe, relative size, divided by the scale factor. And at the present day, that's where you get h0. Naught is subscripts to the present day. And if you plot some measurements from the supernovae, so this is from the Shoes collaboration in green here. This plot comes from Rees et al. 2022. You see that the best fit for the supernova measuring the expansion rate of the universe comes out at about 73 kilometers per second per megaparsec. Now, this is sort of a direct measurement of the motion of using the distance measured from the brightness of the supernovae compared with the redshift, measuring its velocity away, essentially, or how much expansion has happened between us and the time when the light was emitted. And that gives you a 73, so a high H0 compared to Planck. The cosmic microwave background measurements are about 67.5 kilometers per second per megaparsec. And they're now at more than 5 sigma tension. And this is become closer to discoveries. So another way of plotting this is to have a look at how H0 has changed with sort of publication year. you can see we had this blissful time in the 2000s to sort of 2010s when everyone was happy and we agreed our error bars were big enough that we were all very consistent. And then as you hit Planck here, there was this like consistent with, so WMAP, by the way, is the previous cosmic microwave background experiment. So in red is cosmic microwave background, and in blue is distance lateral supernova measurements. And you can see when Planck came out, it was consistent with WMAP, but it dropped quite a bit and had much smaller error bars. And so that's when we started to find these two probes were inconsistent with each other. And it's not just two measurements, there's a whole bunch of different measurements. And here's a summary from Lucia Verde, where you see we've got the cosmic microwave background and large scale structure and Big Bang nucleosynthesis are known as early measurements because these come from the early universe. So the cosmic microwave background is the light that's left over from the Big Bang. The large scale structure is still, it's a measurement of the galaxy distribution closer to the present day. But the Big Bang nucleosynthesis is something also that happened right at the beginning of the universe. And that's scaled the size of the standard ruler that's being used there. So these are sort of early measurements where you fit a global model to the data, and you come up with your values for the parameters, of which H0 is 1. The late universe measurements here are primarily measurements that are direct measurements of expansion. So these are, but the top few are all supernovae calibrated in different ways. You have this measurement here, which is using lensing time delays, which is a super cool measurement. You've got measurements to masers, surface brightness fluctuations, and then the ones down the bottom are all different ways to combine the ones above. And so it's these sort of measurements. You can see the early universe ones tend to be discrepant with quite a few different ways of calibrating things and different measurements. And I know I've gone through those quite quickly without going into details, but I just wanted to leave you with the impression that it's not just like one measurement disagreeing with another. There's quite a few different ways of doing things that are all sort of now need to show us that there's something weird going on. But that's not the only tension. So another measurement that we use in cosmology is this measurement called sigma 8. And that's basically measuring how clumpy the universe is. So how you measure sigma 8 is you take a sphere of 8 megaparsecs, you plonk it over there in the universe, and you measure its density. And you plonk up the same sphere over there, and you measure the density over there. And you do that many, many times. The dispersion in that measurement is sigma 8. So if you have very strong clumpiness and beside voids, then you'll have a really high sigma 8 because there'll be a large difference in the densities of spheres of 8 megaparsecs. Now, this too can be measured in a wide variety of ways, including gravitational lensing. And here's a measurement that was one of the measures. Some of the lensing measurements here in these bananas compared to Planck sticking out here on the right. And this isn't as discrepant as the H0 measurement, but there's a little bit of tension there. A better way to show it, we have S8, which is a combination of sigma 8 and omega m with this equation that's on the bottom left. It removes some of this banana degeneracy and is a slightly more well-behaved parameter to use. And so that's what is shown on the plot on the right. It's the same data, but it shows you the comparison between the different probes a little bit more clearly. So this one's starting to sort of nag at us as well. So this is one of the other tensions that we see. So tensions can be really intriguing. So for example, going back to those things that I was talking about in the 90s, the dark energy tension or the tension that we had then, as I was mentioning, was that galaxy observers said that we had about a matter density of 30% what was required to make the universe flat. And theorists were like, hold on a second, if we're close to flat, we really should be pretty much exactly flat. So where's the rest of the universe? And that one was solved by adding an extra axis to our plot here. You add dark energy. So this one is the cosmological constant version of dark energy, where dark energy is consistent with the vacuum energy or just a constant over time and space. And if you then ask the theorist, what do you expect if you add dark energy in the picture or a cosmological constant, they're like, or they'll be like, oh, we're happy with anything along this red line. That a flat universe includes everything there. And the galaxy observers would be like, hey, well, we can meet you up here if you like. And then when the supernovae, when people went out and measured this, they got a plot that looked a bit like this, where sort of the middle of the contours, X marks the spot. If I move that, my little sketch down there, you basically find that the supernovae were like, hey, yeah, everybody's right. It's flat and the matter density is 0.3. So if you can solve a tension in this way, then you win a Nobel Prize. So obviously people can get very excited about seeing tensions because they're a really cool way to look at resistance. On the other hand, tensions can also just be systematic errors. And we have a long history of, I guess, being slightly optimistic about our error bars in many fields of science. The first measurement of H0 was about a bit over 600 kilometers per second per megaparsec, plus or minus 50 or so. And of course, that was not correct. So that actually made the universe only 2 billion years old, making us the universe younger than the Earth even. But as time went on and calibrations got better, they realized there was miscalibrations in those early data. And really, we were down here somewhere. So if you zoom in on that last little bit of data there, it looks here. So we've been much, much better in the last few decades to be a bit more consistent. But the error bars tend to still be probably a little bit too small. So maybe there's some sort of systematic in the data that we're looking at, and that's really important to consider. Nevertheless, the excitement over these tensions is enormous, and people are coming up with all sorts of cool theoretical solutions to try and explain them away. Here is a set of suggested solutions that have come from the theoretical side of things, with the quantum origin of dark energy interacting dark sectors, changing the sort of environment-dependent electron mass, or something like that. All sorts of varieties of things here. And this was just a small selection from a 6-month window. Here's a slightly larger selection taken from a year where I just basically looked for tensions in titles and made sure that they were cosmology related. So basically, the theorists are having a great time, having a field day, coming up with ideas to explain what's going on here. So some of the theoretical efforts, I should say, fall in a couple of groups. One area of the theoretical efforts is the fundamental physics side of things. So that's like, for dark matter, for example, can we take our standard model of particle physics and add a dark matter particle? Or maybe we don't need to add just a single dark matter particle. Maybe there's a whole standard model of dark matter particles that we need to add there. There could be a whole dark matter chemistry going on for all we know at this stage. And then the other type of theory that's needed to attack this problem is the modeling. So we have quite complex analyses, and we rely quite heavily on simulations to measure or to predict exactly the patterns that we see and deal with non-linearities and that kind of thing. And you need to be able to put all of these together to really understand the data that we're looking at. And so we need both theoretical efforts in the fundamental side and in the modeling side to proceed on the dark energy, on the tensions question. So, okay, so I just wanted to spend a tiny bit of time wondering about whether the tensions could be systematics. And so here's going back to the cosmic microwave background with this beautiful picture that we love. I'm noting that all of these are really complex analysis. So in the cosmic microwave background fits those 30 nuisance parameters. You've got to take into account foregrounds and dust. You've got to subtract the emission from our galaxy. There's stars in the way. So, if you're looking at something back from the beginning of the universe, that light has had to travel through a lot of stuff. And then you also have to take into account the detector sensitivities and that kind of thing, and if there's any changes with time. And so it's a non-trivial analysis to do, and it's been done extremely carefully by extremely clever people. So it's hopefully this is all good, but nevertheless, it's a complex thing. And there's some interesting little tensions even within the cosmic microwave background data itself. So if you recall, I showed you that the WMAP satellite, which came before Planck, didn't have any massive tensions. And then there was sort of a bit of a jump down in H0, so that Planck got a slightly lower H0 than WMAP had. And that the thing that Planck added was more stuff on the small scales. So WMAP had good measurements on large angular scales, where this blue sort of thing is. And Planck added much more data in this small detailed scale side of things. And so if you fit the Planck data just with the large scales, you get one of these blue contours here, which you see is actually much more consistent with the supernovae, which is this yellow band up here. So H0 is on the vertical axis in this top left plot, and the baryon density is on the horizontal axis. And the cold dark matter density is on the right-hand column. And you can see much more consistent if you just consider the large scales of even with Planck. And it's only if you fit the smaller scales, you actually get a much lower H0, like around 64. So it's the combination of fitting these all together that is giving you these small error bars and this H0 a bit low. And so that is potentially worrying, but they're careful in the papers to note that this is not a statistically significant difference, and that it's still a good fit to the data, etc. And so it's not necessarily a problem, but it's one of those things you like. If there's some internal tensions, we still have more to do as well. So going on to the theoretical side of things, one of the cool things that you can do is add all sorts of different parameters to your models. So if you have sort of a different equation of state of dark energy, or if you have a curved universe, you get slightly different answers. Now that plot's impossible to read at this scale, I think. So let me just zoom in onto one of the interesting corners of this, where I've plotted sigma rate, or I haven't plotted, I've taken from their paper, the sigma rate and H0 that you see versus when you add curvature or W to the analysis. This is beyond the sort of standard one where you have the W of, so in the standard analysis, the Planck, they quote the value of H0 when W equals -1. And you can see sort of over here that the main Planck likelihood is actually at a quite more negative W once you allow W to change. This is the equation of state of dark energy. And it would also prefer a higher Hubble constant, which would be consistent with supernova stuff. But the standard model has the cosmological constant being actually a constant, which is the W of -1 here. So that's, if you add more flexibility to your models, then the tension can also go away. Now, type of supernovae measurements are similarly, Sam Hinton made with one of my other students, Hugh McDougall, on where these little sparkles that you're seeing are the supernovae that we discovered with the dark energy survey in these little narrow regions looking out into space. And with the dark energy, when you do supernova cosmology, you have to take sort of quite messy light curves in a bunch of different photometric bands, calibrate them. You have to take into account the fact that the ones that take slightly longer to rise and fall are slightly brighter than those that are quick to rise and fall. And you have to do dust in the foreground and all of these kinds of things. So when we do these kinds of analyses, and this is one of the surveys that I'm involved in, you need to take into account those systematics very carefully. And so in the paper that we wrote on this in 2019, the final data one's coming out very soon. We're very unblinding the results. We had 66 sources of potential systematics that we tracked and tried to quantify to make so that we have the contours that we draw are larger than they would be if we just used statistical uncertainties, because we're taking the covariances of possible errors in the calibration of the brightnesses in different bands, etc., all into account here. Okay, so I think I won't talk for too much longer because I want to leave some time for questions, but I wanted to end with a couple of the cool types of extra data that we're getting at the moment, because in this situation where systematic errors are possible in the data sets that we have, and where people have worked incredibly hard to make sure that those systematic errors are minimized and they're not there, but it's really hard to know what you don't know. So you can measure in completely complementary different ways the same thing, and you find those same tensions, then we'll have much more confidence that the tensions are really genuine things that need explaining rather than systematics in our data sets. So the standard candles and rulers are ways of measuring the expansion, as I've mentioned, and I thought I would talk about one in particular that I love at the moment because it's a very hot topic, and that's gravitational waves. So hopefully everybody's familiar with gravitational waves, discovered in 2015 for the first time. And in 2017, we saw a neutron star merger. The 2015 discovery was a black hole merger. This one that I'm talking about now is merger of two neutron stars, which you would expect to see a kilonova or some sort of bright flash in light after the merger that you see in gravitational waves. And this was a really, really exciting measurement for astronomers. And I think this is my favorite slide of what astronomers did after this gravitational wave went off. Because basically every professional telescope in the world was trying to look at this sort of patch of the sky and find where this optical counterpart or this electromagnetic counterpart to the gravitational wave might be. And the reason this was so exciting was all sorts of cool stuff that you could measure, like does gravity travel at the speed of light? But in the one that I'm most excited about in this context of what I've been talking about is you can use it to measure, because the gravitational wave is a standard candle. They call them standard sirens, but also it's once you see the chirp signal that you get, it's the size, the intrinsic brightness of it. So by looking at how bright the gravitational wave appears, you can measure how far it is away. But unlike astronomy, where getting redshifts are really easy and getting distances is hard, with gravitational waves, getting distances is easy and getting redshifts is hard. So you have to find the optical counterpart to get the redshift. And in this particular case, an optical source was detected. You can see this little bright dot here that was not in the pre-image, and everyone got extremely excited. Now, this one object allows you to put another point on this plot. At the moment, one object has really large error bars, but considering that these other measurements here have had decades of effort, a huge amount of investment, 3 space telescopes in the CMB case, having a single measurement have even this small an error bar is really exciting. And if you take into account some extra details of the angle that you get from looking at radio measurements, that can give you some better details about the orientation of the gravitational wave with respect to us, you can reduce those errors further. And I could shout out to Cullen Howell, who's one of my postdocs, who was looking at the peculiar velocity modeling for this, and we found that their error bars should be maybe slightly bigger, and the values are a tiny bit lower than some of the other papers. Okay, so I don't have too much time to talk about too many more things, but I'll finish with the sort of summary that, yeah, we've got gravitational lensing, clustering of data. We measure the growth of structure. As I said, we measure the amplitude of density fluctuations, and a whole swathe of cool measurements these days with how to test this cosmological model. We look for non-Gaussianities and peculiar velocities and the integrated Sachs-Wolf effect. And I won't go into these. You can ask me questions about any of these if you're interested. I just wanted to flash up that there is a whole bunch of other stuff going on that's all sort of confirming this standard model and is being used to test the tensions. So final slide is that, you know, observing stuff, we're managing to observe the universe in ever more detail, but just observing is not explaining. We can tell you the properties of dark energy and dark matter in quite great detail now. We can tell you how much they some information on both time and position, and we can tell that dark matter is probably a particle and that it doesn't have pressure, and a whole bunch of the properties of these things. But even if we can describe them perfectly, unless we have the theory that explains what they are, we can't say that we understand what they are. And so there is, I hope that I've managed to convey in this little talk sort of the excitement of cosmology at the moment, sort of the excitement of maybe there's tensions, maybe there's, well, there's definitely new theory out there in physics that we need, because we need to explain dark matter and dark energy. It's a really exciting time to be a cosmologist. And so with that, I'll sign off and see if you have any questions.
Okay, thank you very much. Let's thank our speaker for a wonderful talk. Okay, so now it's the time for questions. Please raise your hand and ask your question. The only what I wanted to ask is just please formulate your question in a simple and short way, and no more than 1 or 2 questions per person. Thank you very much. Okay, so let me see. Yeah, so who wants to be the first? Yeah, so I see the hand of Yuri Stanu. Please unmute yourself.
Okay, can you hear me?
Yeah.
Thank you very much for a very interesting, very instructive talk. I think at last understood what the issues in cosmology today, much better. And I'd like to ask you about the systematics of supernovae. There was a talk about 10 years ago or so, or after that, could be connected with their evolution, which we don't really understand, right? Properly understand. Is it still an issue today, or is it somehow resolved? Evolution, environmental issues, etc. For a supernova, which are very distant away from us, of course. Yeah. So
yes.
What's the status of this issue today?
Yeah, so the evolution of, so if you're using something as a standard candle, you need it to be the same in the distant universe as nearby. And obviously you're like, could these supernovae have changed over this era of time? We spend a lot of effort taking spectra of supernovae nearby and spectra of supernovae far away to confirm that the populations that the supernovae are the same in both places. And we're able to calibrate, even if the populations do differ slightly, as long as examples at low redshift are the same as the examples at high redshift, we would be able to calibrate out some of that anyway. The summary is that we don't see much evidence of evolution. We think that if you have what we think the supernovae are generated by, if you have the sort of the white dwarf held up by electron degeneracy pressure, and it tipped over the Chandrasekhar mass and ignites the supernova, you have the supernova explosion. And there's sort of a good physical reason to expect that will always be, pretty cool. We don't expect that to have changed, that physics to have changed over the course of the universe. And the thing that makes the biggest difference is the chemical composition of the progenitor. So the ratio of carbon to oxygen and that kind of thing. And basically the amount of variation of the amount of evolution that you would need to explain the dark energy that we see is enormous compared to what we have. So there could, if there's evolution, it could be having an effect on that, that 1% type of level. It's not something that you could you could get rid of dark energy or anything like that.
Thank you very much.
You're welcome.
Okay, thank you. Who else wants to ask a question? Yes, please. Pergamos, the user with the name Pergamos.
Okay, it's shortcut for my real name. So what is the role of cosmological constant now? Is it enough to explain majority, or you need completely different idea?
Yeah, so the standard model that we have, and I didn't go into this in great detail, sorry, is that the dark energy is a cosmological constant, so that it's constant throughout space and time. And the cosmological constant model does a really good job of fitting the vast majority of our data. I could say all of our data. There's no real strong indications that we need anything other than the cosmological constant. I did show that one plot from the cosmic microwave background where if you have the equation of state of dark energy being, they prefer it to be slightly more negative than -1, whereas the cosmological constant value would be -1. So if I just share my screen again, I'll pull that back up. I'll pull it up first. Yeah. So if you can see that, you can see that this equation of state of dark energy, if it's -1, then that's a cosmological constant. The WMAP satellite was pretty consistent with -1. Planck prefers it a little bit lower. But when you combine this with other measurements, the W of -1 becomes preferred again. So yeah, so basically there's no strong evidence that there is evolution of the cosmological constant with time. So one of the things that I'm most excited about is, so the cosmological constant problem that you probably know of is that if the cosmological constant is due to vacuum energy, so quantum physics says there's vacuum energy, we expect it to have negative pressure, which is exactly what we would need to accelerate the expansion of the universe. But the quantity that's predicted by quantum is, depending on how you calculate, maybe 120 orders of magnitude too large compared to what we see. That's probably the worst prediction in physics that's not infinite. But the thing that I'm potentially most excited about is that if we have a quantum theory of gravity, maybe that can explain why that prediction was so high and bring it back down, much like the ultraviolet catastrophe was solved by having a quantum theory of particles. Maybe the quantum theory of gravity will get rid of this cosmological constant catastrophe.
Okay. Thank you very much.
Welcome.
Okay, thank you very much. Who else has the question? Yes, Mariana Jaber. Mariana, please unmute yourself. Sorry, we cannot hear. Oh, now we hear you. Please ask your question.
Unfortunately, I think that was me speaking.
That was you. Yeah, sorry, your microphone seems to be broken. Okay, maybe in the meantime, someone else can ask a question, and then if you prefer, Mariana, you can just write your question on the chat, and I will read it. Okay, who else wants to ask a question, please?
Cosmology, I'd like to ask one question. Very interesting situations. You show different values of Hubble constant. All physicists who use these satellites, they have high precision. Why so different value? They show 69 to 74.
That's the whole
What do you
question.
think about it?
So you said, I missed a tiny bit of that. You said the like all of these many different probes measure different values of the Hubble constant. So like this plot here, for example.
Yes,
and why are they different?
How researchers explain so big difference?
That's the whole thing, that we can't explain it at this stage. If we could explain it, then we would be able to get rid of the tension. But at the moment, we do not know why these are disagreeing. So as I said, the late time universe ones are the ones that are basically direct measurements of distances and velocities in the local universe. So it's sort of really the more direct measurement of how quickly the universe is expanding, at least close to us. And that's disagreeing with measurements of the global fits to the universe as a whole when you're talking about the cosmic microwave background and large-scale structure measurements out there. So one possibility that's floated is that maybe we are in a slight local underdensity, for example, and therefore our local region really is just expanding faster than the average of the universe. And so this could be just a peculiarity of our location in space. There's been a lot of papers investigating this, and we don't expect a fluctuation large enough to account for this in the standard model. We wouldn't expect there to be a density fluctuation large enough to make the difference that we're seeing here. Also, we don't really see the indication in the supernova data of like a change that you would get to that you would expect for that as well. So it's not like it's not really a favored solution. Some people have proposed things like early dark energy, where you have some non-standard dark energy that happens in the early universe that decays or something like that, which has changed the size of the horizon scale in the sound horizon, which is determining how big how far separated those spots are in the cosmic microwave background, etc. And yeah, but as I said, there's a huge number of models that are being suggested that can theoretically try and explain why these two measurements, or why these series of different measurements, nearby and far away, are different. One thing I didn't go into was I've been investigating whether there is systematic errors in the redshifts, because these nearby ones all tend to be luminosity distances, which when you measure a luminosity distance, you multiply it by 1 plus the redshift compared to the proper distance. Whereas when you're looking at standard rulers, those are angular diameter distances, and compared to the proper distance for those, you divide by 1 plus the redshift. And so that could, if you had a systematic error in redshifts somewhere, then that could be shifting things in the other direction. And it's a surprisingly small difference in redshift can make quite a large change in H0, because you're measuring how far something away is versus how fast it's moving, and the redshift is giving you how fast it's moving, essentially, speaking roughly. And so the redshifts are really easy to measure compared to everything else. So typically they're like, we ignore a lot of the errors on those. And I think what I've found after a long time of looking at this is, again, the redshift systematics probably cannot explain what we're seeing, these differences. But yeah, we're digging in every hole and having a look at every possible thing that we can think of.
Okay, thank you very much
Interesting.
for the answer. Okay, we have a few more questions on the chat. So from Mariana, the first question is, do you have a preferred alternative model type of solution for the current cosmological tensions?
No, I haven't. I don't have one. I am very interested in whether the local measurements, as I was saying, if some local underdensity or fluctuation is biasing, so means that we're not actually measuring the global average for some reason. And as we're getting more and more into precision cosmology, it's becoming more and more important to try to take into account all of the peculiarity of our local universe. So I mentioned peculiar velocities as one thing. You're getting motion within our local universe, and when you use supernovae or the standard candles, you actually have to take into account somewhat how these are moving. And that actually is the answer to your second question here as well, in some extent. Sorry, I'll finish my first one first. Your first question first. In that our local universe affects everything outside that we see. So there's gravitational redshifts, and those are really tiny, we expect, but you know, the light that we see from everywhere is coming through this patch of the universe that we're in. So if there's something unusual here, or as I said, some sort of density fluctuation that's different, bigger than expected, then that would affect everything. So that's one possible explanation. But what I really hope is that maybe if we have a quantum, once someone comes up with a convincing quantum theory of gravity, we'll all just go, of course, and sit back and relax and understand what was going on. Yeah.
Okay, thank you. And the second one is regarding the work of Cullen, remodeling the peculiar velocities. Could you say a few words about what was the reason behind dropping the values in H0?
Mm-hmm. Yeah, okay, so I have a backup slide on this one. So for peculiar velocities, so when you're measuring the gravitational wave, they needed to do a correction for the peculiar velocity. So this is a nearby measurement for which peculiar velocities are important. So this is any motion that is not just due to the expansion of the universe is a peculiar velocity, and that they arise because of gravitational interactions with their local neighbors and that kind of thing. And when you only have, usually if you have like many supernovae or something, that some will be moving away, some will be moving towards you, and the peculiar velocities sort of average out. But when you have only one measurement, the peculiar velocity doesn't average out. And in the case that of this gravitational wave measurement, the peculiar velocity correction was 7 kilometers per second per megaparsec. So it would have been actually even higher if they hadn't taken into account the peculiar velocity of the galaxies. Now, how the peculiar velocities are taken into account is that we actually have maps of our local universe where people have measured how much things are moving and measured the density of these different areas of our local universe and predicted how fast things should be moving based on the densities. And it's those maps that are then applied to the data to remove the peculiar velocity effect. And so what Cullen did was, but basically those maps aren't unique. The original papers used one particular estimate of the peculiar velocity, and it just happened to be on the high side of what all the other measurements would have been. So rather than just taking a single measurement, what Cullen did was do a Bayesian average over all of the different predictions for what that peculiar velocity should be. I mean, they all have reasonable error bars and they're consistent with each other, but they're just like some are slightly higher than the others and that. And once you took into account that, including the extra uncertainty because of that, the sort of variations in that, you ended up with a slightly lower H0. And it was just because the original measurement just happened to take one of the measurements that was on the high side of the peculiar velocity. High or low, hold on, I can't remember perfectly. Hopefully that answers the question.
Yes,
Okay,
thank you.
Oh, now your microphone is okay. Okay, so the next question is from Bogdan Hnatek. Which media correspond to omega equal to less than -1 case? Or if this is just the parameter without some physics behind?
Yeah, what exactly do you mean by media here?
Well, if we say omega is equal to -1, this is vacuum. If it is 1/3, it is radiation. And if it is less than -1, what could it be?
Yeah, so that we give it the name dark energy. Less than -1 can be, you can have phantom dark energy. There are theoretical reasons to disfavor anything less than -1, because you get all sorts of theoretical instabilities that are really not nice. So it may be that we don't actually consider matter densities that are less than 0, and maybe we really shouldn't consider dark energy densities less than -1 because they're theoretically disfavored as well. But yeah, so it corresponds to a dark energy that's essentially increasing with time compared to being just a constant.
Okay,
we
thank you very much.
A really good theoretical, like, vacuum energy is W of -1. It doesn't necessarily map perfectly to something that you can say there's this thing that has that property.
Mm-hmm. Okay, do we have any other questions?
I may ask a question if I'm allowed. This is the second one. If not,
Yeah, sure, please.
Are there any ideas about the structure of dark matter? For instance, if this is continuous medium, it may have waves, and waves may be different from gravitational waves, and maybe we cannot even distinguish between waves of dark matter and gravity. And if there are waves, then you can see in different ways, they move with different velocity, and it partly can explain why you see different expansion.
Yeah, so there's a whole bunch of different proposals for what dark matter could be. And yeah, some of them are cool things like axions, which do have different sort of quantum properties that you see more quantum effects at large scales and things. I didn't show this particular example for dark matter, but this is one of the cool indications that we have that gives us the idea that it's a particle. There's lots of others as well, but this was one interesting measurement where you see what you're seeing in the background here is a cluster of galaxies over here and a cluster of galaxies over here. And when you have a cluster of galaxies, most of the mass in these galaxies is actually in the hot gas that's in between the galaxies. Most of the mass is not in the stars that are shining here. And what people did was they used gravitational lensing to map out where most of the mass was in these clusters. Now, first, this is an image of where the hot gas is. And what these two clusters have done when you look at the velocities, they've actually passed through each other. So this is two clusters of galaxies that have collided and passed through each other. And you can see that by the sort of shock waves that are left in the gas as well. Yeah. Then if you map where the most of the mass is in the galaxies, it's out here closer to where the stars are. And now remember, importantly, that where the most of the mass in the visible stuff is actually in this hot gas. Now, during this collision, the hot gas interacted and got stuck in between these two clusters. Whereas if there was dark matter as a particle involved, dark matter has no pressure. It doesn't bash into itself. It doesn't bounce. It doesn't get stuck. And so it would have just passed straight through and gone out the other side. And so the dark matter, which is the dominant mass total, just pass through. And so what they see is that this is a case where it looks like the dark matter has been separated from the hot gas. And the dark matter was measured by the lensing of light from background galaxy around here. And so these are the kinds of measurements that people are doing to test more properties of what the dark matter particle properties have to be. Don't know if that actually answers the question that you asked, but
okay. Thank you.
Okay, thank you very much. So, do we have any other questions? If not, then let's ask our speaker again for a wonderful talk. Thank you very much.
Thanks.
And yeah, thanks to all of you
Yeah.
for participating.
Yeah, thanks very much for
Okay.
having me. And thoughts are with everyone over in Ukraine.
Yeah, thank you.
Thank you.
Thank you very
Bye-bye.
much. Have a good night.
Bye.
And have a good day, everyone.
Bye bye.
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 Bye-bye.